great to see so many people have turned out for this. I also understand that this lecture is being streamed live to the internet, so I'm even more anxious than just talking in front of you. And it appears on YouTube later on. So all my gaffes and technical mistakes will be preserved for posterity. So if you don't spot any mistakes now, then you can pick me up on them later. So welcome to UCL. Like I said, I'm very glad to see you all here. I'm going to talk about space. I would like to take you on a bit of a journey out to the final frontier of space. Because well, part of the reason I want to do this is because there's a lot of gloom and doom in the world, in the news these days. But my perspective is actually that human beings have just done extraordinary things and carry on to do extraordinary things, develop radical new technologies that actually benefit to all mankind. And that work is going on right now. It goes on in places like UCL, in Cambridge, and Oxford, in the American Space Institutes, NASA. There are astonishing things going on now, and I think we should be really upbeat about these kind of things. So, on to the topic. Einstein was, he developed a number of radical ideas at the start of the 20th century, which at that time couldn't be tested. And now, with the kind of engineering technologies we have, the spaceborne platforms, we can test Einstein's ideas very, very rigorously. But more importantly than that, we utilize his ideas. We use his ideas to make these technologies work. So what I'm going to try to show you in the course of this lecture is the relationship between Einstein's ideas and things that are around us every day. Your cell phones, the GPS device in your car, the kind of spaceborne technologies that we use to measure the way in which the planet is changing. I'm going to show you how all of those technologies hinge upon Einstein's ideas. So here's the great man himself. Einstein was born in 1879. He's got a bigger nose than me, so I think I'm heading in the right direction at least. And he was born of a sort of relatively humble family. His dad was an engineer. And he grew up not as a remarkable sort of child. Actually, people don't quite often realize Einstein was not good at maths at school. In fact, he actively disliked maths at school, and his teachers actively disliked him. So if you find yourself in that category, then, you know, you too could be the next Einstein. Could be sitting here. So what caused Einstein to change? Well, it was a discussion he had with his uncle. His uncle also was involved in engineering. And his uncle told him that mathematics was a bit like a detective story, where X, the unknown quantity, is the villain of the piece. And that caused Einstein to actually become interested in mathematics. And after a while, he realized it was fascinating. And of course, he had a great aptitude for it. But from that small moment of inspiration, we went on to produce one of the greatest mathematical geniuses the world has seen. And Einstein went on to develop these two radical theories, special and general relativity. And those theories predicted things that were very strange. They predicted things that no other kind of physics at that time would suggest was going to happen. Einstein predicted things about the way in which clocks would behave in space. He predicted things about the way in which photons, which I'm going to talk about a bit later on, which photons interact with matter. Now, he predicted those things without an experimental platform to test his ideas. So those were theories. They weren't laws. So Einstein's path through science is very different to Newton's. When Newton produced his ideas, then actually there was an immediate test bed for his ideas. So in his lifetime, Newton saw that he was right, no doubt about it. He could prove that what he did was right. Now, one reflection I had on preparing this lecture about Einstein is some of Einstein's ideas were tested in his lifetime. But what did they give rise to? They gave rise to one of the most destructive weapons systems the world has ever seen, which is the atomic bomb. So Einstein saw his ideas being taken and used. Of course, you can't say that nuclear power is a negative thing, but developing atomic weapons is, of course, in some respects, a terrible thing. And so Einstein had to live with that. So I'm going to close off with perhaps things that I think Einstein would like to reflect upon today in terms of what he did. Now, the next bit is around this guy here, which is Richard Feynman. He's my hero, and he's also a physicist. Now, Feynman said that if knowledge is going to be of some use, it's no good if all it does is tell you what happened yesterday. He said that if knowledge is going to be worthwhile in society, it's going to tell us what's going to happen tomorrow. It's going to enable us to predict what's going to happen. It's going to enable us to build things that we don't yet think are possible. So I'm going to talk a lot about space technology. So the next few slides is a brief introduction to some of the space-borne technologies that I want to talk about. So up here, up in orbit on the right-hand side, we've got GPS spacecraft. Now, GPS spacecraft, they orbit quite far out. So the Earth is about 6.5 kilometers from the middle to the edge. Okay, radius about 6,500 kilometers. And GPS satellites orbit about 20,000 kilometers. They're out here. They're moving at around about 4 kilometers per second. So it takes you and me, well, I'm feeling up to it, about 12 minutes to walk a kilometer. So a GPS satellite goes a kilometer in a quarter of a second. Of course, we use GPS satellites to work out where we are on the surface of the Earth. And I'll explain a bit more about that later. Then we've got what we call low Earth orbiters, like this one over here. Now, these are used to measure the gravity field, and they're used to measure how sea level is changing globally, and they're used to measure how the ice caps are changing. So all critical environmental measurements. Now, the low Earth orbiters, they tend to be a bit closer to the Earth, maybe about 1,000 kilometers off the surface, about here. They're a lot smaller than this, bear in mind. And they move really, really fast. They might move 8 or 9 kilometers per second. Now, in all these technologies we're talking about, measuring environmental measurement or navigation technologies like GPS, we need to know where these spacecraft are out in space. And we also need to know what the distances are, sometimes between spacecraft and sometimes between the spacecraft and the surface of the Earth, what we call tracking stations that try to determine where the satellites are. So I'm going to talk about those ideas, how we measure ranges between spacecraft, and how we work out where satellites are out in space. Because if we're going to get knowledge and science out of these technologies, we need to know those things. We need to know distances between spacecraft and between the Earth and the spacecraft, and we need to know where the satellites are out in space. And what I'm going to show you is how none of that would work if it hadn't been for Einstein. So a bit more detail on these technologies. GPS, well, I'm sure you're all familiar with GPS these days. It's in TomToms, it's in mobile phones. And, of course, that in itself is a miraculous technology. I always try to tell our students that you can just flip one of these things on, and then in a few seconds, you know where you are to within a few meters with respect to the center of mass of the Earth. And that in itself is miraculous. It would have taken us, 20 years ago, it would take several weeks of setting up optical instruments to measure where the stars are, and hours of calculation. Now all of us can just flip on a device and work out where we are within a few seconds. But actually, if you've got the right techniques and you know how to utilize the data from the satellites, you can work out where you are to within a few millimeters. And you can use that information to determine how the planet is changing shape over the course of years, which informs the earthquake cycle. It helps us understand how tsunamis happen. So this is a map of velocity vectors of the continental plates, entirely derived from GPS data. And that's how we work out where the big earthquakes are going to occur. That's how we work out how strain builds up along subduction zones. All of that comes from GPS. So GPS isn't a technology that tells us where we are at a few meters. It can tell us where we are at the level of a few millimeters. The low Earth orbiters enable us to measure the changing surface of the sea. And they enable us to measure how fast sea level is rising, how fast it's falling. Now, this is an example of an El Nino determined from a low Earth orbiter. And that's how we discovered El Ninos, by using low Earth orbiters. But in order to measure that El Nino, which is a sort of a wave of warm water moving across the Pacific, takes quite some time to do that. It's about 20 centimetres high and about 1,000 kilometres across. We have to know where the spacecraft is up in orbit at the level of a centimetre to get that kind of resolution. And that kind of data, understanding things like El Niños, has led to a lot of understanding of how the world works from a climate perspective. In this example, what I'm going to say is this. When an El Niño occurs, warm water moves across, like so, and that displaces the jet stream. It moves northwards, and it changes the entire shape of the weather systems for the next year or 2 years afterwards. And we now know that in the late 1920s, there was an El Niño, and that caused this catastrophe known as the Dust Bowl. And the Dust Bowl was, how did the Dust Bowl happen? So because the rain didn't fall in the Midwest, it fell in the Canadian Rockies, that meant that the grain basket of the US didn't receive the rain it needed. And so you couldn't grow crops, the topsoil was blown away, and it was an environmental disaster. So the coupling actually of the Wall Street crash, which was an economic disaster, and the environmental disaster caused by the El Niño led to the Great Depression. But now we know what an El Niño is. And we would not have been able to do that. We would not be able to understand or measure an El Niño without the spaceborne technologies that I'm going to talk about. So, like I said, the problem is working out where is the spacecraft. That's kind of the question. Where is the spacecraft? How far away is it? What are its coordinates? So we're going to look at two problems. One is how to measure the distance to a spacecraft. And I'm going to show you how we do that, achieving a ranging accuracy of between a centimetre and a millimetre. Then the second part is to predict the orbit of the satellite, to say where it's going with time. And we're going to try to explain how we can do that at the level of a few meters to a few centimetres. So those are the two problems we're going to deal with. And I'm going to show you that we couldn't do any of that, at least to the kind of levels we need to do it, without Einstein's ideas. So, first of all, the range between a spacecraft and a tracking station. So how do we do that? Well, here's the trick. Most of these spacecraft carry clocks on board, so they know what the time is. But these aren't any old clocks. These are atomic clocks. Now, the first atomic clock was invented in the National Physical Laboratories in Teddington, not far away from here. Now, what's special about an atomic clock is how accurately it can slice time up into little bits. So a conventional clock is actually the ones on your watches and so on. They might slice time into a second. That's its division of time. Then it adds up lots of seconds, and it tells you what the time is. Now, an atomic clock can take a second, and it can slice it up into at least 1 million pieces. Actually, the latest atomic clocks can do that to 1,000 million pieces. So it can break up a second, and it can tell you accurately what's the time now within that division of a second. Now, those clocks on board the spacecraft are used to generate signals that the satellite sends out. And those signals have got a very, very precise frequency. So if you could hear the signal coming down from the satellite, it would do a sort of type effect. And that's, the higher the pitch of that, then the higher the frequency of the signal. And that's what the atomic clock enables us to do, to generate a very, very stable frequency. And that frequency is used to broadcast a signal from the spacecraft down. Now, carried on that signal, you can think of it as being a time mark. As the signal comes out from the spacecraft, it says, I sent this signal, and it looks at its watch and says, the time's now 12 o'clock. So you can imagine that the satellite, what it broadcasts is a signal, and on that signal is a little mark saying the time on my clock is now, say, 12 o'clock. That signal travels through space, and then it arrives at the tracking station. Now, the tracking station has also got a clock on board. So when the signal arrives, the tracking station looks up the time on its clock, and it says, okay, that signal's now arrived, let's say at 12:12. So when it picks up the signal, it can see that that signal was transmitted at 12 o'clock. So the difference between what the tracking station clock says and what the time mark on the signal tells you the propagation time of the signal through space. It tells you how long the signal was going through space from when it left the satellite and was picked up by the tracking station. So we've got, if you like, the time of flight of the signal. This is where the first of Einstein's ideas comes in. Because if we knew how fast that signal was traveling, then time multiplied by speed gives you distance. I think most of you can probably get that one, right? There's more maths later, brace yourselves. So time times speed equals distance. So how fast is the signal traveling? Well, the signal is traveling at the speed of light in vacuum for most of its path. And the speed of light in vacuum, 3 times 10 to the power of 8, or 299,792,458 meters per second, that constant speed was predicted by Einstein. That idea was not understood before. Of course, we had to figure out what the speed was, and that's an engineering problem. But the science was that a radio signal in space will travel at a very particular and constant speed. And so we know that. So if we know the speed, and we know the time of travel, we can work out the distance. So the whole trick about ranging between a spacecraft and the surface of the Earth involves 2 clocks. One up in space, in the spacecraft, and another clock down on the Earth. Now, that all sounds very simple, but of course, it wouldn't work under normal circumstances. Now, why wouldn't it work? Well, we come back to Einstein's ideas again. This time, we're going to have 2 clocks down on the Earth. Now, if I've got 2 clocks on the surface of the Earth, they're both running at the same speed. Let's say they're fantastic clocks, they're atomic clocks, and we can compare one to the other. And they're reading the same time the whole time. Good, all working. Now, what if we put one of the clocks on a spacecraft and send it up into orbit? So the first thing that Einstein predicted was that if one clock is moving relative to another, then the clock that's whizzing away out into space will start to run more slowly than the one on the Earth. So the clocks are no longer synchronized. The clock in space is running at a different rate to the clock on the Earth. Now that was predicted through special relativity. General relativity also said that the clock up in space compared to the clock down on the Earth is going to be affected by the mass of the objects nearby. So if you have a big, massive object like a planet close to the clock, and take another clock out here, it's much further away from this, then the clock that's further away is going to run faster. So, special relativity says the clock runs slower. General relativity says the clock runs faster. Okay, if we apply those 2 ideas together, they don't cancel out. That'd be good, wouldn't it? But they don't. So, Einstein's theories predicted how clocks would actually behave in the space environment. It predicted how much slower they would run and how much faster they would run. So how much of this is a big deal? Well, let's use GPS as an example. If we didn't take general and special relativity into account, then per day, we would start to get our understanding of time wrong by about 38 microseconds. Okay, that sounds like a tiny amount. But remember that the distance that we're measuring to the spacecraft is the speed of light times the time. So if we've got time wrong by 38 microseconds, that means we're going to get the distance to the spacecraft wrong by a whopping big 11 kilometres. So that would mean that all this attempt to position things at the millimetre level, well, that's just a laugh. That just wouldn't happen. Actually, you couldn't even use GPS to position your car or even to go rambling. It just wouldn't work. Now, interestingly, when the US Air Force paid for GPS. Now, they didn't invent it. A bunch of scientists and engineers invented GPS. But so initially, these scientists said, well, you're going to put atomic clocks on the spacecraft and fly them at 4 kilometers per second, 20,000 kilometers away. So if you do that, then those atomic clocks are going to go wrong by something like this every day. Do you think the Air Force believed them? No, they didn't. The Air Force wanted an Einstein switch on the spacecraft, so that if Einstein was wrong, they could just switch the spacecraft back to operating like a normal clock. So you can just think of it like some big, a big spanner on the side of this spacecraft. Einstein was wrong, right, okay, back to normal physics. But actually, as it happens, Einstein was quite right, and that's what you observe. So You make the corrections to the clock based on relativity, and then you measure the range of the spacecraft, and everything works out. Now, you might say at this point, well, how do you know it works? Because if you can measure the range to a spacecraft using clocks, but somehow the clocks are wrong in some kind of way, how do you know it's right? Well, one way we've got of validating that is to fire lasers at the spacecraft. And we bounce laser light off the spacecraft, time how long it takes for the laser to come back again, and then we time that round trip. And you can do that with quite a cheap clock. A little quartz oscillator will do for that. And we find agreement between our ranges based on the clocks compared to the lasers. And how well does that agree? Well, that agrees at the centimetre level. So we think it all stacks up. Okay, so that's explained a little bit about the relationship between GPS and spacecraft ranging and clocks. So we looked at general and special relativity where clocks are concerned, and we looked at the speed of light in vacuum as being a constant. In the next step, I'm going to talk about photons. Now, before we can get there, we have to understand a little bit about how technologies like GPS work. Now, how it works is that the satellites are flying around up there in orbit, and the US Air Force has got tracking stations on the surface of the Earth, and they're measuring ranges of satellites all the time. Now, from those ranges, they work out where the satellite's going to go in the next few hours. And they turn that into a little mathematical formula, and they upload that to the spacecraft. So once the spacecraft has got that formula, it can predict where it's going to be with time. So as the satellite's flying around, it's using that formula to work out where it is going to be in the future. And then it broadcasts a signal down to you saying, here's where I am in space, because it's a predicted orbit. I know the time, it sends that down as well. So it sends down some information saying where the spacecraft is and what the time on its clock is. And if your little device can measure ranges to 4 or more spacecraft, then it can work out its position. I'm not going to talk about that. But the key thing is, for GPS to work, we've got to be able to predict where the spacecraft are going to be in the future. Because in real time, the spacecraft has to say, here's where I am right now. That's what it's got to do. So, what's the relationship between photons and working out where a spacecraft is going to be in the future? And that's to do with using physics to write down equations that tell us what the forces are acting on the spacecraft. Because if I want to know where a spacecraft is going to be in the future, if I know all the forces that are acting on it, and I can write down equations that describe those, I can say where it's going to go. It's a bit like me saying, if I poked the Earth with my finger in a certain direction with a certain speed, then I can say it'll go off in that direction. And that's the trick. It's writing down equations that describe forces on spacecraft. So, what are the forces acting on a GPS spacecraft? Well, there are quite a lot of them. The first big one is Earth gravity. So, and that's quite a complicated thing in itself, but we think we know about that. We know about the mathematics. We can describe the Earth's gravity field very well. Then you've got the gravity field of the Moon and the Sun. They simply pull on the satellite and change its trajectory in space. But now, in terms of a hierarchy of magnitudes, in other words, we're going down to smaller and smaller forces, the next one is a bit of a surprise. It's the radiation from the Sun, and I've got to explain that in much more detail in a few seconds. But you've also got, because the spacecraft heats up from this radiation hitting it, then it emits heat, and that causes a force. We've got radiation, electromagnetic radiation, light and heat, hits the Earth, is emitted by the Earth, bounces off, hits the spacecraft, that pushes the spacecraft in its orbit. The spacecraft itself is transmitting signals. Those are photons. As the photons are pushed away from the spacecraft, there's a recoil force, which is that's Newton's third law. So as the photons are pushed away from the spacecraft pushes back in the other direction. And then we have tidal effects, and then a few things, general relativity and some other planets. Okay, so let me explain about photons. So, I'm sure you've all seen Star Trek, and you all know what a photon torpedo is, right? So, how many of you think a photon torpedo might actually work? Hands up if you think a photon torpedo might work. That's me and Alper. And nobody in my group put their hand up. That's terrible, right? So could a photon torpedo work? Well, you're going to know the answer. If you get one thing out of this lecture, it's how a photon torpedo would work, right? It's worth staying awake for, I can assure you. So what are photons? Well, actually, this room is full of photons. Photons are little blobs of electromagnetic energy, blobs of energy. So the light coming from my tie that you can see, the only reason you can see it is because photons are coming off my tie continually, and they're hitting your eye and exciting the rods and cones and sending a signal through to your brain. But photons also come from heat. As my body is at a certain temperature, the whole room is at a certain temperature, then there are photons coming out of everything continually. The microphone systems, the microwave systems here, that transmission is all based on photons. So why aren't we falling over because of all these photons hitting us? Well, because the forces are so tiny. But you'll see in the space environment, it becomes a bit of a problem. Now, here's the issue. How can photons actually cause a force? How does that work? How does light actually hit something? Because that's non-intuitive, right? Well, here's the math slide. Because that's from Einstein's special theory of relativity. Now, I'm sure you've all seen that equation before, E equals mc squared. Now, what is that? Well, the m is the mass of a particle, and c is the speed of light in vacuum. So the energy that particle has is E equals mc squared, and that's what they used to develop atomic power and atomic bombs. That was the idea that it was based upon. However, that's not the whole story. That's a slightly more complete equation. Now, I'm not going to go through all the terms, but the key thing is that rho term there is the momentum of the particle. Now, for a photon, the m0 term is 0. So a photon has no mass, right? No mass at all. But it does have momentum. Now, what's momentum? Now, you might know intuitively what momentum is, but in physics, momentum is the product of the mass of an object times its speed. And so something that's big and is moving fast has got lots of momentum. Something that's light and moving slowly doesn't have much momentum. So when a truck hits you, you know. Now, so that's what momentum is. So momentum is related to force. So if momentum is transferred to a body, it feels a force. And what Einstein's theory predicted is that although a photon has no mass, it does have momentum. And because it has momentum, when a photon hits something, then it will transfer that momentum to the object. It will be absorbed, and then you'll feel a push. Now, we never bother about that. We never think about that in mechanics on the surface of the Earth, but in space it's different. So radiation from the sun flies through space, hits the spacecraft, some of it bounces off, some of it is absorbed. Now, those photons cause a transfer of momentum to the spacecraft, and they cause a bit of a push. So if we could work out where all the photons are coming from and which parts of the spacecraft they hit, we could add up all that information and work out the resultant force on the spacecraft. Now, some of those photons cause the spacecraft to heat up, and those photons are emitted back out into space. And as they are emitted from the spacecraft, they create a recoil force. So that as the spacecraft heats up and emits this radiation, there's a push on the spacecraft as well. Here's the question. How big are those forces? What difference do they make? Well, on the table in front of you, you've got one of these. Okay? So could you all pick them up, pass them around, and just feel how heavy they are? Feel them pushing down on your hands. Okay, so that's a force of about 1 Newton at sea level. So imagine how much smaller that force would be if you cut it in half. Okay? Be a lot less, right? Cut it in half. So the first order force on a spacecraft due to the sun, you'd have to cut that into 10,000 little bits. So imagine how much that's pushing down on your hand. It's a tiny, tiny force. Now, if we want to actually try and describe those forces mathematically, they're going to help us position the spacecraft at the level of a few centimetres, then we actually have to divide that into 1 million bits and then mathematically describe the push from those photons. So it's 1% of the first order force. So this is the problem of mathematical modelling. So we do that. That's just one of the things we specialize in my group. We sort of create mathematical models of spacecraft, and we simulate photon fluxes using pixel arrays, and we work out which parts of spacecraft the solar radiation hits, and then we work out how much momentum is transferred, how much radiation bounces off, how much heat is transferred, and then we add up all those, and it gives us a resultant force on the spacecraft. Now, we use computer technology to model realistic geometric spacecraft. Every single component on the spacecraft, we create mathematical models of those, and we use quite sophisticated models of the interaction of the radiation with the matter to work out resultant forces. So we can work out which bits are shadowed, where the radiation goes afterwards. We then mathematically flip these pixel arrays all the way around the spacecraft, and we build up a kind of mathematical function, that means a mathematical formula, that describes all the forces acting on the spacecraft. That includes the radiation coming from the sun, as well as radiation coming from the Earth. And it becomes quite a complicated problem, because the Earth is emitting lots of different kinds of radiation at different frequencies and at different intensities in different directions. So it's computationally quite a difficult problem. So how well does it work? Well, what I'm going to show you now is our orbit error based on how sophisticated these models are that we're using to describe these forces. So in the first one, if we just use all the gravity forces we talked about, and we model solar radiation pressure, then after about 12 hours of the satellite being in orbit, our orbit error, that means our inability to predict the orbit, might be around about 8 meters. So this is modeling all the gravity forces and solar radiation pressure. If we include thermal radiation, then that orbit error after 12 hours drops quite dramatically. Carry on, add this antenna thrust, that's the radiation emitted by the spacecraft, goes down again. If we include the Earth radiation, it almost flatlines. Now, so if we do all this mathematical modeling of the forces on the spacecraft, we can predict where the satellite's going to be 12 hours from now within 10 centimetres. That means the satellite's flown 173,000 kilometres through space, and yet we can say where it is to within that. And none of that would work if it hadn't been for Einstein's laws. None of this was predicted by anybody else. It was Einstein's idea. So for us at UCL, in my group, we've worked on these ideas quite some time. We work with the US Air Force, and we work with NASA and the European Space Agency on these kind of problems. I thought I'd give a little bit of credit to my group. There are most of them are over here. And those are the people, they work on relativistic models of clocks, they work on photon pressure on the spacecraft, they work on all kinds of positioning applications with these kind of devices. So this subject area where we work in, I thought to say a few things about that. It's called space geodesy. Now in space geodesy, it's about measuring planets from space. But it was relatively unknown science until it appeared in the Doctor Who annual about 4 years ago. Question number 20, what is the science of measuring the gravity field of a planet from space? Space geodesy. So I feel finally I have some credibility to come and give a lunch hour lecture. Okay, so briefly my conclusions. But these spaceborne technologies enable us to do things today that would have seemed miraculous 20 years ago. We can work out where we are on the surface of the planet to within a few meters, even to within a few millimeters. We can do that in real time. We can work out where a spacecraft is up in orbit. Maybe the spacecraft is 1,000 kilometers away, moving 8, 9 kilometers per second. Well, we can work out where it is to within 10 millimeters. Now, that's not just meant to be a sort of, ooh, wow, core blimey, mate, type thing. Actually, we can use those technologies for the benefit of all mankind, for environmental measurement, for logistics, for security. And none of those ideas would work if it hadn't been for Einstein. Einstein's theories of special and general relativity underpin all of the science that makes that engineering possible. So I think that if Einstein had been alive today, I think he would have been pretty chuffed, actually. I think he would have looked at that and he'd gone, great stuff. So next time you're using a smartphone or a TomTom to position yourself, or you're looking at some report on sea level change or how the ice caps are changing, I think tip your hat to Einstein. Thank you.
Thank you very much, Marek. We have time for just a couple of questions. Has anyone a question? Right, here.
Yes, what I wanted to ask is this. Yes, I just wanted to ask this. When a signal leaves a satellite, initially it's travelling in a vacuum. Mm-hmm. Before it reaches the tracking station, it has to come through an atmosphere of ever-increasing density. Do we have to take that into account, or is the effect negligible even on the very small scale we're working at?
No, it makes a big difference. So the question was, how does the atmosphere affect the speed of the transmission of the signal? And we have to model all of that. Now, there are various tricks we can play by observing on multiple frequencies to get rid of some of the effect. But essentially, we have to model that as well. And the delays can be as much as 80 meters in terms of a distance.
Is it easy to explain why Einstein's two theories say that the atomic clock in space should be going both quicker and slower than the clock on the ground?
Actually, I think special relativity, when you look at it, you have to write down a thing called the Lorentz term, square root 1 minus v squared upon c squared. And that's not too difficult, actually, not too difficult. I think general relativity is much harder. I wouldn't be able to give you I mean, Santosh, I could refer you to my student, would help on that. I think general relativity is harder. But I think what we get in my group, for example, because we rely upon this stuff every day, we get a kind of, like a faith in it, because it works so well. So I think that a quicker route to understanding, or at least confidence in the theory, is to look at experimental data and go, right, I plug in the models, and my word, it works.
Any more?
Have any qualms about the measurement from CERN that at the moment is suggesting that neutrinos can travel faster than light? In fact, I mean qualms about the geodesic technology.
Yeah. Well, it's funny because actually, Trish and I were talking about that just actually at the start. I don't believe it in the slightest. Not to say that an object couldn't travel faster than the speed of light. The key thing is if it goes through the barrier. If you try to take, because what the equations tell us, if you start with an object and you make it go faster and faster and faster, as you approach the speed of light, then you end up dividing your formula by 0. And we know everything from engineering, from science, tells us that's a no-no. Now, what if you could jump, though, over that? What if there was some kind of quantum effect that meant you could jump over the speed of light? Okay, it's not impossible. However, with the CERN experiment, I think that's one experiment. And if we look at the data coming from supernovas, looking at the arrival time of neutrinos versus the photons, there's a lot of evidence that says the speed of light is not exceeded. But, and also, I think that story was jumped upon by the media, to be honest, actually. I'd be quite skeptical.
One more question over here.
Yeah, I was just thinking about the radiation of the sun and it not being as constant as it fluctuates hugely. How do you take this into account with your work?
So you're quite right. The radiation of the sun changes. There's a thing called the solar cycle, and it varies between 9 and 14 years. And the radiation of the sun goes up and down by about 0.4% in the solar cycle. But because we've got satellites sitting at a place called L2, Lagrange 2, there are observatories, there's one called SOHO, and now there's SDO, the Solar Dynamics Observatory. They're measuring that radiation flux continually. So we have a great source of data that tells us how those things vary. But you're quite right, we do need to take that into account, because it does change over time.
I think we have time for a very, very quick one.
I don't want a hard one.
Yeah, thank you. Are you saying that today's space age would be unimaginable without Einstein having lived when he lived? Because
yeah.
I mean, if he was alive today, he wouldn't have lived when he lived, and we wouldn't be in the space age.
That's exactly what I'm saying. What I'm saying is that actually none of this, if we hadn't had an Einstein who predicted all these things and gave us the mathematics that describe how things behave, we couldn't use these things the way we can today. We could have something, but it really wouldn't work anywhere near as well. And that's I think, is the really inspiring thing about Einstein. He started from humble beginnings, wasn't even that keen on mathematics. And it gave us this framework which enables all this technology. But I would also like to encourage people to come and work in science and engineering. So any of you, actually, it's pretty cool, We wave our geek flag high, and we get to do some pretty neat things these days. So any of you, if you're thinking about a career in science technology, okay, it's not big money. My wife will tell you, right? But it's a great life, and we contribute, we feel. Okay, thank you.